I'd like to do two things today. I want to finish sections 1, 2, and 3 in Chapter 12. Those sections deal with experimental design. And then we will talk a little bit about the exam, which is next Monday. So just to let you know where things are. We did a little bit of review in the first week on some probability ideas and some introductory material. And I believe Chapter 3 is on the binomial, and so we did that along with learning a little bit about R Studio and R Markdown and the R language during that first week. And technically, Chapters 8 and 9 could be considered review, but we may have covered it in more depth, and we certainly also used R to cover the material, which you probably didn't get if you took Stat 511. So there may be a little bit on Chapter 3, but most of the exam will start in Chapter 8. And my intent is to go through section 12.2. And 12.2 is something we'll cover today. We'll also cover, hopefully, 12.3, but my intent is not to have that on the exam. What I'd like to do is actually go back and cover that material in 12 and then come back to discussing the exam. But just so to make sure that I don't get cut short, I want to give you a little bit of material now, and then I'll come back and talk about the exam at the end a little bit more. So, Chapter 8 was on the two-sample t-test. Chapter 9 was on the linear regression with just one variable. Chapter 10 deals with analysis of variance topics, and in particular that was for the fixed effects model, and that had a lot of material in it for doing multiple comparisons, things of that sort, pairwise comparisons, contrast. And then Chapter 11 got into not only fixed effects but random effects, but still within the context of only a single, on the right-hand side of the equation, only a single factor, be it fixed or random. In Chapter 12, we're getting into more complex situations where we're modeling, we're trying to model a response variable, a continuous response variable in terms of more than one predictor. In this case, more than one factor. So that's sort of where we are. Now, to give you an idea of what you will and will not be doing, usually I'll do something like this. I'll say work 10 out of 11, and you can work all 11, and I'll drop your low one, or you just skip one. It may, depending on how long each question is, it could be 8 out of 9 or 10 out of 11. It depends on the length of individual questions. You will not be using the computer. It will be a paper exam. And so, since you won't be using a computer, to the extent that it's computation, that it will be very simple computations. You won't be computing a lot of sums of squares and stuff like that by hand. That would just chew up time and not add to substantively to anything. So, so what might I ask? My exams tend to be short answer, so I have a question and maybe part A, part B, whatever, and they tend to be short answers. So what types of questions might I ask? Well, it could be R output, and I ask you to interpret it, or I might ask you to extend it a little bit. Again, computationally, it would be very little, but I might want not only interpretation, but I might want to know what certain terms mean. terms of computation, one of the things I could do is give you analysis of variance. If you look in the book, they may have an analysis of variance table and certain pieces are missing. But you have enough information to compute those pieces if you understand how you compute mean squares from sum of squares and degrees of freedom and so forth. So, and also how certain sums of squares add up to other sum of squares, so you can fill in the pieces by subtraction and so on. So I may give you an analysis of variance table with some missing pieces where you have to calculate things. Again, there's some examples in the book, particularly in chapter 12. You should know what the assumptions in a model are. And in some cases, a lot of cases, we talked about how you check those assumptions. You should know the expected mean squares and why the f-tests are constructed as they are. In other words, in these cases, if you look at the numerator expected mean square over the denominator expected squared, under the null, that ratio typically is 1, under the null hypothesis. And so statistically, you would expect the f value to be, if you actually get estimates of those expected mean squares with the actual mean squares, then you would expect that ratio to be about 1 under the null. Or at least you don't expect it to be too big. And we use a critical value to say what's too big, or we compute a p-value. You should know concepts. What are the shortcomings of Fisher's LSD versus the HSD? But what are the shortcomings of the HSD versus some of the other methods for pairwise comparisons? What are the limitations for the HSD in terms of sample size? So the conceptual information, I might ask you to contrast between different types of multiple comparisons. When would you use one over the other? So there'd be concept-based questions where you have to explain things. So those are the types of questions that I will ask. It's possible that I could say, write the R code to express a certain model, for example. Now you're allowed to have one sheet of paper front and back. When I say a sheet of paper, I mean 8.5 by 11. So I do that for a couple of reasons. One reason is that it forces you to organize the material, what's important, what's not. I'd recommend that you use the space carefully, but don't try to make it so small you need a magnifying glass. You'll spend all your time looking for stuff. So you want to organize it well. The other reason is that, there are a lot of formulas and things to remember, and so I'm not particularly interested in whether or not you remember all the formulas. For example, expected mean squares, conceptually you should have some idea of how they're computed. Later on we're going to have some rules of how you compute them in a standard. There's some standard rules for computing expected mean squares. Once you go beyond those kind of nice cases, such as if you get beyond it, such as unbalanced designs, then computing the expected mean squares becomes extremely difficult. This is one thing that I must say that I like JMP, is that they compute the expected mean squares. And so you can get some idea that if you have unbalanced designs, then when I said the ratio is equal to 1 under the null, that's not necessarily true of unbalanced designs. And so you reach a situation that your f-tests are only approximately true. And depending on the degree of unbalance, you can get some sense of, well, how bad is that approximation? And there are also ways to construct what are called synthetic f-tests, and we'll talk about that later. Let's try to line up the expected mean squares better. I'm not sure. I'm not sure how to get expected mean squares in R. That's something I wanted to look into. It's not built into the base R, but it's possible that someone has developed a package that does it. There's a package that tries to mimic what SAS does, and it's possible they do it in that package. That's something I'll probably show you that package at some point. So, are there any questions? Yes.
Should we bring the calculator?
It might not be a bad idea. Most of the calculations are going to be pretty simple, but if you want to, you can bring a calculator, but not a smartphone.
Okay. So, also, I have another question. Do you think the assignments are very useful as the review thing?
Yeah, I think the assignments are, and I will be giving you. Let's see, I posted 10, right?
Yeah.
I'll be posting 11 before the weekend, so you can take a look at the problems at least to get an idea of the ones that I think are important. So, in terms of some of the problems are important, but that's not 100% true because right now, probably maybe 2/3 of the assignment problems I'm oriented towards data, and maybe 1/3 towards, using R as either a calculator or how. In other words, some of them don't have the raw data, and so therefore you can't use the LM function and so forth. You can still use R if you want. That's sort of up to you in those cases, although I want the information put into the homeworks electronically, of course. But you can use R as a calculator, even in those cases that the raw data is not available. But I maybe weight it a little more heavily towards the database problems as opposed to the ones that aren't data-based. But actually, it might be the reverse of that on the exam because I can't give database problems unless I say, okay, here's the R code, this is the output, tell me what's happening. I can do that, but I can't have you run the R code. So I think it's good to look at the homework. I made when's the due date for the, Chapter 9 is actually due this Friday, but this isn't due until after the exam, and I'll be putting Chapter 11 here, and it will be due the following week. So in other words, we have, this Friday, next Friday, and the following Friday, we all have assignments. Then things may stretch out a little bit more. Chapter 12 is a long chapter.
So the exam is just Chapter 8 to 11, not Chapter 12?
Well, I was going to have the first 2 sections of Chapter 12.
Thank you.
Yes.
Are we allowed to use our book on the exam?
No, just a sheet of paper. That's why I want you to organize the material. So it might be a good idea to bring a calculator. It's not essential. I'm not going to have you compute anything that's going to be very difficult to compute. But if you want to bring a calculator, you can. But you can't use a calculator on a smartphone or a tablet or whatever. But yeah, the one sheet of notes, no book, one sheet of notes front and back. Okay. So I would think about how you want to organize it because it's a very good study aid. Developing that sheet is a good way to study because it forces you to think about what's important. It's one of the reasons I do it, as I said, that it forces you to organize the material in your mind.
So we can have answers to exercises, but would it be fair to put like the disadvantages and advantage of the different multiple
You can
comparisons?
put whatever you want. You can put answers to exercises if you want. Yeah, I'm not restricting what you put on that sheet. Yeah.
So just reading the book is the best way to prepare for it, I think.
It's a good way.
Okay.
Read my notes, the book, look at the R code, how you do the R code, what the R code means. Yeah, all of those things. The notes by themselves, you know, I talk, I don't say every word that's on the notes. So the notes, I'd say, are a necessary but not sufficient condition. The book gives more detail and gives, so the fact that I, you know, didn't cover something, I mean, the book may cover in a little more depth than I covered in class, so you should read the book. There was a couple things I skipped. I didn't cover Duncan's new multiple range test, and I didn't do much with student Newman calls. I did a little bit. But a couple things I didn't cover in the book. I didn't cover I'm not going to cover the non-parametric stuff. I decided that we're just not, you know, I'd welcome you to look at it, particularly if it's important to your discipline, and know the non-parametric techniques, but I'm not going to cover the non-parametric techniques on the exam, so you can skip those. And they tend to be the last section in any chapter. So you can skip the non-parametric techniques. I started covering it, I think, early in the term, but I decided not to, just because of time constraints. We do have a non-parametric course 551 if you're interested in that in more detail. If you don't have time to take that course, the material in this book gives you some basic ideas of how to do things. Any other questions? Or maybe at the end, if you think of something at the end, we'll come back to that. So what I'd like to do now is go into RStudio. And so here is, by the way, these notes cover the first three sections, I believe, and I'm going to actually split those apart into separate notes. But I haven't done that yet, so the notes here you can use. Okay, let's knit this. Now we've covered a lot of this. I'm just going to go back and review it. And then we'll go into section 2 and 3. So section 1 deals with nested designs. Sections 2 and 3, section 1 is nested. Sections 2 and 3 deal with experimental design, which controls variability. Nested designs are not so much in terms of controlling variation. They deal with a couple situations such as subsampling. If, for example, I have certain treatments that get applied to individuals or patients, then the patient or individual is the experimental unit. So you always need to think about what is the experimental unit. The experimental unit is what you apply the treatment to. So if you actually apply treatments to something, that something are the experimental units. Now, given that I do that, well, you could have different populations and you're sampling from each population, and those would be the experimental unit. The populations would be the group differences, or the groups. Now, given that I do that, if I apply treatments to certain individuals, I could also subsample those individuals to get multiple measurements, and that's often done. So, for example, if a tree is given if you spray a tree with a certain type of insecticide, let's say an orchard, and you're looking at trees, you may sample several spots on the tree. So you have tree-to-tree variation, and you have sampling within tree. Or if it's a human and you're doing blood tests, you may apply a treatment to a person, but then you may have multiple blood tests on each person. So again, the person is the experimental unit, the multiple tests on an individual are the subsamples that you do. So this is a type of situation we're doing. Now it can go further than that. I mean, you can have samples within subsamples, and so, in other words, you can have your samples, which let's say are the experimental units, and then you can have subsamples within those experimental units, and then you can have subsamples. So the nesting can go further than I've let on here. We're looking at the case where we just have one more level of sampling, but you can have more than that. So be aware that nesting can continue on down to lower levels. So in our model, mu plus alpha sub I plus beta sub ij, notice there's no effect that only has a subscript j. It's not like alpha sub I plus beta sub j plus c sub ij. There is no effect that only has a subscript j. And that is because j is specific to an I. In other words, the subsamples j are specific to an I. So put it another way, if you have multiple blood samples from the same individual, there's multiple blood samples. For the ith individual, you get, say, 3 blood samples over time or whatever. Of course, if it's over time, that may be effect of interest. So, but and we'll talk about that case later. But so, in other words, J, which represents the subsamples, are specific to I. Now, in the book, they have a tree-like structure they show. And so you sample the experimental units, and then within each experimental unit, you get subsamples. And so there's a tree-like structure they show in the book, a hierarchical structure that gives you some indication of how that works. Okay, so that's why there is no effect that just has J. Now the beta is going to be a random effect. I'm not interested in the specific subsamples. I mean, first of all, they're specific to a particular individual. Now, the alpha, which is the treatment effect, could be fixed or random. So you could have a completely randomized nested design in which you have a main effect, the treatment effect, which is random, and then the experimental units within that are random, and then the subsamples of that are random. So it could be completely random, where everything is random, or it could be that the main effect, the treatment effect you're interested in, is fixed. That depends upon, the nature of those treatments. Am I interested in those specific treatments, or do I have a sample of treatment effects that I'm interested in from some larger sample? So the assumptions are the sum of the alpha sub i's equals 0. Now again, I say that's an assumption, but in reality it's the way we define it. Now R doesn't do it that way. R will set alpha 1 equal to 0. It actually uses the first group or the first treatment as a reference, and then everything is compared relative to it. But again, in terms of the F-test, the multiple comparisons, it doesn't really matter how you define that constraint. You get the same F-test. So the alpha sub i's, if they're random, we're going to say they're independently normal for mean of 0 and variance sigma squared sub A. And then the beta sub ij we'll assume they're independently normal with mean 0 and variance sigma squared sub b. We're also going to assume that if the alphas are random, that the betas and alphas are independent of each other. So in other words, the effect due to subsampling of the experimental unit effect is independent of the treatment effect. And likewise for the epsilon sub I jk, which is the subsample, it will have an independently normal mean zero and variance sigma squared. Now, of course, these normality assumptions are just that, they're assumptions. Of course, it gets harder to check these types of assumptions for these random effects models. But at any rate, we're interested in testing that either the alpha is of 0 for the fixed effects or that the variance sigma squared sub A is 0 for the random effects model. There is a sub-hypothesis, and that's sigma squared sub B, the experimental unit variability is 0. That's the secondary hypothesis. So you might ask the question, you're going to see, well, let me come back to that in just a moment. If you look at the definitions, if you're looking at the treatment variation, they're looking at the treatment mean minus the grand mean, and you're squaring those and adding up over the treatment levels. And likewise, for the experimental unit variability, you look at the y bar sub ij, averaging over all subsamples, minus the mean for that group, y bar sub I, and you're looking at that variability. And the total sum of squares is just the yijk minus the grand mean squared over everything. There are computing formulas, t minus the correction factor, a minus the correction factor, b minus a, and t minus b, in order to get all of these quantities where the t's, the cf's, are defined below. The t is simply the sum of squares of everything. The correction factor is the sum of everything squared over the number of observations, which is a times b times n, when you have a balanced design. And by the way, you don't have to have a balanced design. The number of experimental units could vary from treatment to treatment, and in fact, the number of subsamples could vary from within each treatment, within each experimental unit, I'm sorry. But the formulas I've given assume a balanced design. If it's not balanced, you can still do it in R or SAS or whatever. You can still run these analyses. However, if you do that, these nice expected mean squares aren't quite so nice. You don't have n's and b's, and it's not that nice. And it's much harder to compute those expected mean squares. For the nice cases, I'm going to show you how to compute it. There's some sort of simple rules, and based on those simple rules, you can actually write out those expected mean squares. And we're going to do that, I think it's in section 4 of chapter 12. So once we get back, it will come pretty quick on how you compute the expected mean squares. Again, for balanced, nice designs. If they're not balanced, it's not so easy, but that's something I will show you how to do in JUMP, is how to get the expected mean squares, and that can give you some idea of whether or not there's some issue in terms of the f-test that you're using. Now, so you might ask, if you look at the among treatment, is there a treatment effect? Either the alphas equals 0 or they don't, or if it's a random effect, sigma squared sub A, is it 0 or not? You can see under the null hypothesis, then you want that ratio of expected mean squares to be 1, right? So what do you think you're going to use as the error term for testing the treatment effect? There are two possibilities, the among experimental units or the among samples within experimental units. By the way, that notation, I'm saying the parentheses, what I mean is among experimental units, parentheses means within treatment. And then the next one says among samples within experimental units. That parentheses notation means within, what's in parentheses. So, what do you think I'm going to use as my error term for testing the treatment effect? Now remember, in the null hypothesis, I want the ratio to be 1 for the expected mean squares. Well, if the hypothesis, let's take the fixed effects. If all the alphas are 0, then this term drops out, right? And then these two are the same, so that ratio would be 1. Likewise, under the random effects models, if this is 0, if sigma squared sub a is 0, then again, these two are the ratio are the same. If I would use the among samples of n experimental units, then I would expect even under the null hypothesis, I would expect the f-test to be greater than 1 because of the sigma squared sub b effect. So because of that, I'm going to use among experimental units among experimental units within treatments to test the treatment effect. And if that's my main hypothesis, and my secondary hypothesis is the sigma squared sub b is equal to 0. And again, if I set that to 0, then these two have a ratio of 1, which would indicate that I would use among samples within experimental units to test the among experimental unit variability, the secondary hypothesis. So this brings up a question. If you're looking for degrees of freedom, do you want B to be bigger or N to be bigger? This is a mistake a lot of people make. They get a lot of subsamples, but B is small and N is not so small. But you see, that doesn't help you very much because the degrees of freedom, in order to get power, you need, in the denominator, you need enough degrees of freedom. So if you want power, that is, you reject when you should reject. When there is an effect, you reject. You'd like to reject. If you really do have a treatment effect and you want to detect it, then you want high power, high probability to detect that effect, given it's really there. That's power. But since you're testing the treatment effect with the experimental unit in treatment, the power is, to a large degree, going to depend on how big B is. So if you go out and only sample a couple experimental units per treatment, but then you get lots of subsamples, that doesn't help you very much. You see what the problem is? So you have the denominator degrees of freedom in this f-test is what's critical for power. And if B is not big, your denominator degrees of freedom will be small, and therefore you won't have power. Is that clear? So when you're designing it, this is always the struggle between statisticians and researchers, is it costs money to get the B's and less money to get the N's. That is, to get experimental units you apply the treatment to can often be expensive. But then to get subsamples from that experimental unit is often not so expensive. That's not always true, but a lot of times it is. And, I may have given the example, of the Exxon Valdez, and I said, okay, the experimental unit is the beach. Beaches are expensive to get. Getting samples on that beach are not so. Once you're at the beach, getting more than one sample is not that expensive. But the distances and so forth, and just the whole process of laying it out, and the weather, and et cetera, it's very expensive to get the beaches. But the experimental unit is the beach, not the samples on the beach. If you would use the subsamples as your error term, sometimes what people will do is the following. They will test the experimental unit variability, the secondary hypothesis, and if you fail to reject, that is, you're saying that sigma squared sub b is 0. Well, if that's 0, then you would say, well, these disappear, and why can't I just use the subsample variability, or better yet, pool these two and use the pooled estimate, pool these two, and use that as my error term. So I could take the among experimental units among samples and pool those together and use that as an error term. That's called pseudo-replication, by the way, and it's frowned upon. It's not to say that you can't do it, but the problem is this. That your secondary hypothesis, if you say, I fail to reject, that's not quite the same as saying I accept, because you don't know what the power is. If, in fact, you strongly reject, just the opposite. if in fact you're pretty certain that you have high power and you fail to reject, even though you have high power, then you have a stronger case for pooling those estimates and then sort of engaging in pseudo-replication. So you can defend it, but it becomes more difficult to defend. Now, obviously, if in fact that's true, then I can combine the degrees of freedom for both of these, and I get a much larger sample size. So just be aware of that. Pseudo-replication is a term you're probably going to hear. This is an instance of it. If I would use samples within experimental units as my error term for treatment, or if I pool the experimental unit, the last two, the experimental unit with the samples within experimental units, pull them together as one term, which would basically say I just fill, in R terms, it's Y tilde treatment, and just leave everything else in the error term. That would automatically pull everything together. If I just say Y, whatever Y is, tilde treatment, and leave nothing else in the model, then that would automatically pull everything into one error term. But again, you need to be very cautious about doing that. So here we have an example of taxis. We have 5 types, 2 cars, and n equals 3 tests per car. And so here's the first 6 observations. And again, here we're doing type plus, and this is R's way of doing it. It's slightly different the way you do it in jump and sass is slightly different. So I have miles per gallon tilde type, and then plus type slash car. That means car within type. That's a nesting. I've nested car within type. In other words, the car is specific to a type. Car 1 of type A is not the same car as car 1 of type B. They are different types of cars. They couldn't be. Okay? Now notice that R tests things incorrectly. If you look at the mean squares, if I divide the 32, it's dividing it by 0.2. So what R is doing is using the residuals to test both of these. Now the 1.4, that is the mean square for the type colon car, and the F value is 7. That's correct. That's the secondary hypothesis is correct, but the primary hypothesis is not correct. It's using the wrong error term. So at any rate, in order to do that, we need to divide, the actual F test is 32.1 divided by 1.4. So this divided by this gives me the true test. And if I do that, the actual F value is 22.6. So now again, that 7.1 is okay, and there are the critical values. See that? So you see that both are significant. Now those critical values, I showed you how to find them right here. You can find them from R, or you simply can use R to compute the p-values. We could have done that. We could have computed the p-values. There's another, that QF computes the quantiles, but the probabilities can be computed from PF. In other words, F is for the F distribution, QF is for the quantiles, PF is for probabilities, DF is for density, and RF is for a random sample of Fs. So there are 4 functions. With every distribution in R, there are actually 4 functions. So you have the name of the distribution, like in this case F, and then you precede it with either a Q, a P, a D, or an R. In this case, we're getting quantiles. For the critical values, it's a Q. If I would have got the p-value, I would have needed a P to compute probabilities. I'll probably add that just to show you how to do it. Now, in terms of the means, the only reason I did this fit 2 is I modeled by type -1 the -1 takes out the intercept, and that actually just computes. That says, okay, instead of using the mu plus alpha sub I don't have a mu, I just have an alpha sub I. And in that case, the alpha sub i's are actually the sample means. So those are the sample means. The coefficients are the sample means in that case. But I can also simply get it by using a by statement. I'm going to, and this is a common thing, I want the means of miles per gallon based on type, by type. So in R, this by construct is very common. For example, in SAS, it's been around since the earliest days of SAS back in 1970. And the by statement in SAS is very common. In R, this is the way it looks, miles per gallon, comma, type. So type is a categorical variable, so I want the mean for each type, the mean of miles per gallon for each type, and that's how you do it. And so again, those are the means for the groups, for the 5 means. And you can see they're the same as above. But I wouldn't use the above in general. Using the method here is better. Now, I have an outer product. I'm getting the outer product of means, which forms a matrix. The outer product of something, the outer product of a vector with a vector will be a matrix. So instead of having, if I take the outer product of a vector of length 5 with itself, I get a 5 by 5 matrix. But what's in the elements of that matrix? Well, that depends on that operator, which in this case is minus. So it's going to get all pairs. What the outer product is going to do is get all pairs. But in this case, I'm going to take differences of pairs. If I had an asterisk there, it would get products of pairs, but I'm not interested in that. I'm interested in all pairs. So if I'm doing pairwise comparison, I get all pairwise differences, right? So that outer product is one way of doing it, and I'm just rounding off to 3 decimal places. And so those are the differences. So if I'm doing Fisher's LSD, those are the differences. So without getting an absolute value, so what that table is, it gives me all possible differences. Now I only need really I only need the lower part. The diagonals are 0 because if I take the first mean minus the first mean, it's 0, right? The second mean minus the second mean is 0. So the diagonals are all 0. And you notice that the upper diagonal is sort of the negative of the lower diagonal. So I don't need the upper if I have the lower or vice versa. So typically you would just need the lower triangular part of that matrix. And those are the pairwise differences. How many of them are there? There are 5 things taken 2 at a time. There are 5 treatment groups taken 2 at a time, so that's 10. 5 factorial over 3 factorial times 2 factorial, which is 5 times 4 over 2. 10. So there are 10 differences. And so, but now the key is what do I use to test? Well, if I look at the t-value, if I look at, if it's a 2-sided test, I'm looking at 1 minus alpha over 2 for the t, and the degrees of freedom will in fact be 5. Why? And the mean square I'm using is mean square for B, not mean square for E. Because I'm testing, again, I have to test with the B effect, not the subsample effect. So each mean is averaged over B times M things. In other words, y bar 1 dot dot, how many things am I averaging over? Whether, in this particular example, there are B cars per type, and n equals 3 tests per car. So I'm averaging over 6 things for each mean for each of the 5 treatments. So that's where the 6 comes from. This 2 over 6 is because we have a balanced design. I'm taking a difference. And so I'm getting the variance of the difference is the sum of the variances divided by the sample size. So since it's the sum of the variances, the 2 of them, that's what 2 comes from. So I'm using mean square for B, which is 1.43, I hope. Let's go up and look. Yeah, it's this value right here. So I'm computing it, and this is from R, and I get a 1.77. Then I can look up here and see which ones. If I look at the absolute values, I see which ones are bigger than that. Now notice this one right here isn't quite bigger than that. So that's technically A versus C is not significant, although it's very close. But a lot of the others are, not all, but there are a number of them that are greater than 1.77. Again, I'm taking the absolute value. So if I compare those 10 numbers, to 1.774, I can see which ones are different. Now remember at the end of chapter 10 where we held all those pairwise tests and we had a table with p-values? So instead of having that table, we actually could use R to construct a table of those p-values. There's actually a way to do that in R that's more direct because R uses this internal function which creates this table of p-values. So there would be a way of doing this more directly. I'm showing you sort of the nuts and bolts of how you do it. But again, we're using mean square for B, for the multiple comparisons or pairwise comparisons, because B, and mean square for B, is the error term for the treatment effect, not the mean square, FE for it. So if I estimate the variance components, again, from the expected mean squares, if I look at the expected mean squares for this model, I can see if I take this minus this, I'm left with NB. So if I divide that difference, if I take the mean square of B minus the mean square of E, and this isn't quite true because the mean square of B is actually an estimate of that full expression. But in a sense, it looks like if I take the difference, then that would leave N times sigma squared sub B. And if I divide by N, that should estimate sigma squared sub B. And likewise, I could just use the mean square error for E to estimate sigma squared. So those are the two variance components. Of course, if I wanted a variance component here for A, if I wanted a variance component for A, I would take the mean square for the treatment effect minus the mean square for the B, or the experimental units, and then I'd take that difference and divide by B times N to get the variance component estimate of sigma squared sub A. So there's a certain logic to that. So this is how you estimate the two variance components. Now notice that the variance component, the car-to-car variability is about 0.4, whereas the test within car variability is about 0.2. So there's about double the amount of variability from car to car than test to test within a car. That's often the case. That if take blood samples from a person, the blood in a human is actually fairly homogeneous. So if I took 3 blood tests in a fairly short period of time, I'd probably have much less variability than I would from person to person. In other words, whatever I'm measuring with respect to blood would vary from person to person a lot more than the same samples within an individual. Well, that's the case here too. It's about double. So a lot of times we are interested in how much variability. Now, a lot of this came from genetics, where you were looking at genetic variability. We're trying to find which traits were causing a variation. So in genetics, estimating the variance components was extremely important because you were trying to identify sources of variability. Now I'm gonna show you this, but I'm not going to go into detail today about this LME4. We're going to come back to that later in this chapter, and I'm going to explain in more detail. This is a very complex package in R for doing mixed models. And so I'm going to talk about it a little bit more later in the chapter because we're going to use it again when we get to some more complex models towards the end of this chapter. So I'm going to come back to this particular thing. I'm just going to say that there's a function called lemma, or LMER, which is in the package LME4. The LM, what we're talking about here is we're looking at linear mixed models. Mixed models means that you have both random effects and fixed effects in the same model. Now that's could be true here because our treatment effect might be fixed, whereas our other effects are random. But here, this is a little strange. I have miles per gallon is modeled as type plus 1, and then I have vertical line colon type, and that's colon is an interaction operator. So I'm nesting within sort of the overall grand scheme of things. The 1 represents sort of a intercept term or an overall effect. I'm nesting within that the interaction effect. And it turns out, and again, I'm going to get into this a little bit later on about how this works later in the chapter. It turns out that this lets us partition the model such that we can attest for the fixed effects as well as get the variance component estimates directly. And so in this case, I call the fit taxi fit 2. And that's based upon this more complex model. And I can apply, if I apply the ANFA to that, it actually gives you, notice that it correctly gives you the F-test for the fixed effect, or that main hypothesis. In other words, there are 4 degrees of freedom. There are 5 types, 4 degrees of freedom. A minus 1 is 4. And the mean square is 4.54. And notice the F value is 22.6, which is the correct F value. Remember, when I did this before, that was done by hand. This did not give the correct, that's just running it naively like this did not give you the correct F-test. It gave you 161.06. That's not the correct F-test. That was dividing by the subsampling mean square as opposed to the correct mean square, which was the experimental unit mean square. So, in other words, it used the test-to-test variability to test the treatment effect or the type as opposed to car-to-car variability. So I was using the wrong error term there. That's what R did by default. To correct it, again, you can use LME4, this package, and that will allow us to get the correct test here. But it also, notice here, if I now do a summary of that fit, that summary will give us it gives a breakdown of both the random effects and the fixed effects. And notice for the random effects, it gives the variance components. And so the 0.409 and the 0.201 right here are directly computed for you. Now, it is using REML, R-E-M-L, which is what REML means, it's a restrictive maximum likelihood estimate. Remember I said that if I use these naive estimators we did above, the naive estimators were given right here, where I simply took the difference and divided by n in this case. There's no guarantee that the mean square for B is bigger than the mean square for E. So therefore you could get negative mean squares. The REML estimates force it to be positive. Now in this case, if I get a negative, I simply set it to 0. Basically I'm saying it's very small. So I kind of have to correct it after the fact if I get a negative, whereas the REML will put a constraint on it so it won't be negative. In other words, during the estimation technique, they put a constraint on it. That's why they called it a restricted maximum likelihood estimate. When you get into maximum likelihood estimate, what you're asking is, what values of the parameters maximize the likelihood function? So given the data, what parameters are most likely to, you can think of it this way intuitively. Given the data, what parameters are most likely to have generated that data? We can think of it that way. Now mathematically, it can get a little bit difficult to compute these maximum likelihood estimators. Generally speaking, for normal models, they're not that difficult. Okay, so this is the REML model. Now it also gives the estimates for the different types, and from that you can get the mean estimates for those models. Okay. Down here I show you that type A will simply be the intercept. In other words, R by default is setting alpha 1 equals 0. And so based upon that assumption, then type A will simply be the 14.83, which is type A, which is the intercept. Type B will be that intercept plus the alpha beta effect, which is the 3.217, and so that mean is 18.03, and so forth. So the mu plus the alphas will give you the B, C, and so forth, and the mu will give the A. Now, of course, you would have computed that differently had you used the sum of the alpha slots equals 0, which we could have done. So, at any rate, this is this is nested design. I'm going to spend a few minutes going into the randomized complete block design, but because I'm not going to cover this whole topic, the exam will stop. This should be 12.2. Okay, the randomized block design is 12.2. I'll correct that. But the point is, the exam will stop at 12.1. I'm going to spend a few minutes introducing you to block design, but I'll stop it at nested designs since I'm going to have about 10 or 15 minutes here. So what's the idea of a block design? A block design is it's a situation where you have a lot of variability and you're trying to figure out ways to control that variability so that you can look at the treatment of interest and be able to test it with more precision. Put another way, you want to reduce the noise in the system so that the signal comes through. So if there is a treatment effect, you want to be able to detect it. So what we've done before, like when we did the one-way analysis of variance, we could call that a completely randomized design. We have treatment levels, and we either assign those treatments to individuals selected at random, or whatever the experimental units are, or we have populations and we sample from that population at random. Those are called completely randomized designs. Randomized complete block is we have blocks, and each treatment appears in that block. So for example, I say, suppose we have B farms, and we have A varieties of corn. And suppose on each farm we have all the varieties of corn. If that's the case, then for a particular farm we have all the varieties. And so you can think of it as we can compare the varieties within a farm and then pool the farms. And so we remove the effect due to the farm. And if there's a large farm-to-farm variation, then if we remove that, then the error term is more pure. So for the classical block design, randomized complete block, or RCB, we're going to have each treatment appearing only once within each block. Or in this case, each variety would appear only once. So you would have one field of variety, the first variety, another field in the same farm of the second variety, and so forth. But only one. Now, you could break that rule, but typically we do it that way. So in R, we could have y sub ij tilde variety for the randomized completely randomized design, or we could have y sub ij tilde variety plus farm. In this case, the farm is the block effect. So by modeling farm, that gets removed from the error term. You see, in the first model, that farm-to-farm variation is in the error term. But in the second model, farm is removed, so the error term hopefully is a better measure of the true variation that we should use to test corn. Test a variety, I'm sorry. So the farm effect is almost always a random effect. It could be fixed, but it's almost, you're generally not interested in a specific block. I'm not interested in the specific farms. I'm interested in the variety differences. So it's almost always the case that the block effect is random. I mean, technically it doesn't have to be, but it almost always is. So here's the model. In this case, you have mu plus alpha sub I plus beta sub j plus epsilon sub ij. And again, I'm assuming a balanced design here. So y sub ij is a response of the ith treatment within the jth block. And we're going to, typically the treatments would be fixed, but they could be random. We could have selected the varieties from a large collection of varieties. And so we either have the sum of the alpha sub i's equals 0 for fixed effects, or the alpha sub i's are independently normal, mean zero variance sigma squared for random effects. The beta sub j's, as I indicated, in essentially all cases you can reasonably think of they're a random effect with some variance sigma squared sub b. So they're independent normal, mean zero variance sigma squared sub b. And the epsilon is your error term, independent normal, mean zero variance sigma squared. I'll just quickly show you this model, and then I'll see if there are any going back a few minutes on the exam to see if there are any questions. So here I'm. By the way, this contrast statement is saying that for factors, I'm going to use the contrast sum, the sum of the alpha sub i's equals 0 type thing. The second one says, what if they're ordered factors? So if you had A less than B less than C, so if you had ordered factors, that is, the levels were ordered, then that contrast dot polynomial would be orthogonal polynomials that you would construct. So those are sort of what we're going to use in this case. And so if I read in, say this is a psychology experiment in which you have 4 subjects, and each subject is administered 3 treatments. So each subject gets the same 3 treatments, and so therefore there's a crossing. Each subject sees each treatment. And therefore we can treat the subject as a block. And we have 1 treatment for within each block. And so you record the length of time to complete a task. So if we do that, how many observations do we have in this particular case? We have 12, right? 4 times 3. We haven't replicated, so there's not an n here, so we don't have, some sort of replication in that sense. In fact, here you really couldn't. So if we have 12 degrees of freedom, how does it get broken out? Well, there are 4 subjects, so B minus 1 will be 3. So there are 3 degrees of freedom for subject. And treatment, there are 3 treatments, so A minus 1 is 2. So you have 3 degrees of freedom for subject and 2 degrees of freedom for treatment. And the residual will actually be the product of those, A minus 1 times B minus 1. And so that has 6. Now if I add that up, we get how much? We get 11, right? And the other one would be for the intercept. So the corrected total would be 11. That correction factor has 1. And so that's it. There are no other degrees of freedom. Now, if you think about it, you might ask the question, suppose there's an interaction between the subject and the treatment. And we're going to talk about interactions a lot. Well, in other words, instead of writing the model mu plus alpha sub I plus beta sub j, perhaps suppose the alpha and betas can interact, so there's an alpha beta ij. Well, then you have a problem. If there really is an interaction between the subject and treatment in this case, it's confounded with the error term. And so confounding is another key word, just like pseudo-replication, to take away from today. Confounding is very common. In this case, it's kind of unavoidable. Now, there is a way around this a little bit, and we'll talk about that. I don't have it in my notes yet, but I'll talk. In fact, it's not in the book. I'm going to talk about that a little bit next time, that there is kind of a way that we can, there is a little bit of a way we can deal with the issue to determine whether or not we have an interaction effect. But if there is an interaction effect, then our F tests are a bit wrong. They're too conservative. And I'll start there next time. So there's a few minutes left. So I'm going to take off next time. So just to reiterate, in Chapter 12, we will cover nested designs. We will not cover block designs. So up through 12.1 will be what the exam covers. So are there any other questions going back to the exam? Just to I did a little bit on the binomial. It's possible I might ask the question. Whoops, I didn't mean to do that. It's possible that I might ask the question on Chapter 3. But most of the material will be 8, 9, 10, and 11 in the first section of 12. So what other questions do you have about the exam? Do most of you have the homework back? As I mentioned, I will be posting the homework I'll be posting Chapter 11 homework later this week. So you can take a look at the problems. They're not due for a while, but the one is due this Friday. Okay, well, next Monday. For those people that are distance-based, since they can hear me, I'll be making arrangements with a proctor if for those that cannot come to Morgantown and take it here. So I'll be emailing those folks. Any other questions? Okay. Yes.
So the exam will be in this room, correct?
It will be in this room next Monday at the regular time. Again, any distance-based students that are nearby can come here if they want, or optionally, I'll set up a proctor. Okay, see you next Monday. I don't know. I don't know for sure whether or not we'll get back to Chapter 9 graded. Maybe. It might be, maybe on Sunday. I'll have to see it. I'll tell her about it so we can have the work problems. And then, there might be a chance during the weekend you'll get back to graded 9.